Yeah.
Host new Nairobi HIV.
Good morning. Hello.
Morning, how are you?
Fine.
Yeah. Morning, how are you?
Good morning once again. I'd like to welcome us all to our DRT CME series that is set to unfold for this month. I'd like to request a volunteer to start us off with a word of prayer. Anybody to volunteer to give us a word of prayer as we start? Tuanze kwa maombi. Alatina, could you pray for us, please? Oh, Peter, I see you unmuted. Please go ahead.
All right. So good morning, everyone. My name is Peter Omulo. So let's bow for a word of prayer. Our Heavenly Father, we honor you. We give you glory and thanks this morning. As we are starting our engagement this morning, we want to ask you, Father, to give us wisdom. May you bless each and every one of us doing in the interest
Yeah, I'd like us to go right into it. My name is Dr. Muti. I coordinate the TWG, the HIV TWG in Kajiado County. I'm also the county mentor and the regional chair for the TWG. We shall be having Chris take us through the introduction to DRT. DRT has become an important component in the management of our clients, and we want to see how best we can offer our services to them with the resources that we have. So Chris, as you know, is your mentor and also the regional coordinator, the regional TWG coordinator. So I'll invite Chris to take us through as I remind us to please put our gadgets on mute and to share any questions that we have in the chat, so that as we proceed, we shall address them when the time comes. Asante. Karibu, Chris.
So thank you, Daktari, and thank you everyone for joining this important CME. I have a bit of a flu, but I hope I'll be able to cover this topic excellently so that we are able to pick the most important point and we are able to also cascade this to our colleagues who will not be able to join at the meeting. So I hope you can hear me. And in case I have any trouble with my internet, I'm in the office at STC Casino. We just got connected to the internet, so I'm not used to it. In case I'm lost, kindly let me know. For those who are, kindly let us try and mute so that we don't interrupt the CME. We intend to take exactly 1 hour so that we keep, when we keep time, we also encourage people to join our subsequent CME. So we are planning to have a series of CMEs that are supported by UN Faria Jami project. So today we'll be doing introduction to HIV drug resistant, just an overview of what it is when we talk about HIV drug resistant testing. And then on Wednesday next week, we will have Collins Temesi from NASCOP take us through the orientation to the online ULISA NASCOP platform. I will also talk briefly on how to fill a clinical case summary. That's I've seen some people do very excellent clinical summaries. Others do some very poor clinical summaries. But of course, that is because of the knowledge gap, and we intend to sensitize everyone so that we're able to make good clinical case summaries that even if you send to someone who is not in Kenya, can be able to review and give feedback. Then the other CME that we will do, which will...
Chris, I see you're back. We lost you there for a while, almost immediately.
Let me move to somewhere where I know the internet is much better. Give me like 1 minute.
That's fine.
So sorry about that. I think in the right spot. Yeah. So I was explaining. I was just explaining what is in front of you. That we will have a follow-up CME on the overview of genotypic and phenotypic HIV drug testing, and this will be the lab aspect of drug-resistant testing, which will be covered by an expert in the field, Elfas Okapesi from UON HIV DR lab. Then I will now come back after you have understood how the tests are done in the lab. I will come back and now to talk about the DRT mutation one by one, the mutations, the impact of that mutation, and why it is very important. Then the last, I'll focus on that day. I will focus on NRTIs. Then the other, the last CME will focus on NNRTIs. They are still relevant. I know we no longer use NNRTIs we no longer use them as we used to because of the phase out that we did for nevirapine and of course efavirenz. We have still a few patients on efavirenz, but remember, we still have patients who are on that line on etravirenz, and retipivirine is a molecule that is coming as an injectable, long-term injectable in future. So we still, the NRTIs are still with us even in the future. So the time is much gone. I want to go straight to the CME or the topic of the day. So allow me to stop sharing this so that you can go straight to the discussion. Yeah, so that is the topic of the day. So introduction to HIV drug resistant testing. We're just giving the overview of it. And I'm the one who is doing the presentation. I'm the coordinator for the Nairobi RCWG and the Nairobi County Clinical Lead Mentor. So I want us to start by knowing the basic of HIV life cycle. Why is it important? It is important because these ARVs, they target a different part of or different stages of the life cycle. So it's important to understand the life cycle in details, so that we are able to even understand the mutation. We understand how the ARVs works, and that is very, very key. So I'll start with this one. I know it's not the first time we are seeing this this slide. So basically, the life cycle of HIV is the steps flows as follows. So there is, of course, there is attachment, there is fusion, there is entry, then the reverse transcription occurs, whereby there is RNA to DNA, then there is integration. I will go through each and every step in details. Then there is transcription, translation, assembly, maturation, and budding. And this is very, very key to understanding the target, the ARV, where the ARVs target. So let me start with the first part here. Let me look for my pointer, because it is very important to see what I'm talking about. I hope you can see the pointer, Daktari.
Yes, we can.
Yeah, so I want to use the pointer to help me elaborate and describe, to elaborate why it is very important. So so you see this part here. There is a yellow thing. This yellow. So this yellow ring here describes, or it's the viral, the envelope that carries viral DNA material or RNA materials or genetic materials for that matter. And it's very important because once it attaches, and there's a process of attachment or fusion, and the fusion occurs when the HIV virus envelope attaches to glycoprotein 120 and 41 that helps the virus to release the genetic materials into the CD4 cell. So the round thing is the CD4 cell. Then let me use the pointer. So the first thing that will happen after the fusion has occurred, there's attachment, entry, and fusion. The fusion after the fusion has occurred, these genetic materials will be released to the CD4 cell, inside the CD4 cell, and the viral RNA and reverse transcriptase enters the cell. Then there is a process of now the transcription whereby the DNA copy is synthesized by the enzyme reverse transcriptase, and this is followed by the RNA now degraded, whereby a second, remember RNA is single strand, while DNA is a double strand. So there will be formation of a double strand, a second strand, making it a double strand, which makes it a DNA. Now, once it is, the DNA is formed, the viral DNA is formed, it integrates the part here, it integrates with the human chromosome. Now, this is inside the human cell nucleus, where the genetic material of a human are located inside the human cell. So this part here, the yellow part here, represent the DNA, that the viral DNA that was produced at this point. So there will be integration, and then there will be, so once it integrates with the human chromosome, the next part will be, so it will integrate, then the following process will follow. The first process that will follow is what you call a transcription. And transcription basically means the DNA is now converted back to RNA. Remember, that is why it is very, very critical to understand the life cycle of the virus, because at this point, if this one has occurred, the integration, the viral integration to the human chromosome has occurred, then you cannot reverse the process. And that is why we give a PEP before the integration occurs. So before 72 hours. So you expect after 72 hours, integration has occurred. That is why if you give a PEP after 72 hours, then it will be useless because integration has already occurred. So after that, the transcription occurs, which basically means now the segment of the DNA is made or is used to make the viral DNA. So basically, you will produce the virus will produce the RNA and the RNA messenger cells, which are very, very critical for the next stage, which is translation. And translation basically means production of proteins. So there will be a protein, a sequence of amino acids will be formed, which will basically form a large complex, which is then translated. And this process is done by the cells called ribosomes. So after translation, there will be viral membrane protein will be transported to the host cell membrane, so that now there will be budding and maturation. And after so there will be assembly, then budding and maturation, and the cell and the mature viral. So this one is basically similar to what entered the cell, but now it will be released to attack other CD4 cells, and through that process, the replication occurs. So there will be production. So the one CD4 cell is able to make very many copies of the virus. Basically, the whole idea of HIV infection is not, the virus itself is not necessarily, the aim of the virus basically is not to cause any harm, but just like any other organism, just like you and me, is trying to survive. And in the process of surviving, it only attacks, it has high affinity to CD4 cells. So what it does to the CD4 cells, it converts the CD4 cells into a factory of making the viruses. So the virions, the viruses, and in the process, the whole idea of the CD4 cell being an immunity cell is eroded. And because of now overworking to produce the viruses, then the CD4 cell will be overwhelmed and it will die. So in the process, that's how we lose the CD4. So basically, this is how it's just a repetition of what we have just covered, but now focusing on where we use the ARV starts. So we have fusion, the fusion inhibitors, the likes of the likes of drugs like enfuvitin. Then we have the likes of Maraviroc, which basically is a CCR5 receptor, chemokine receptor antagonist. So we also have drugs like reverse transcriptase inhibitors, such as the likes of tenofovir, zidovudin. We have integrase inhibitor. That the process is to stop the process of integration, which is of course aided by the integrase enzyme. Then we have protease inhibitors, and we also have something that is coming up very soon. What we call maturation inhibitors. So this one is undergoing clinical studies, and soon we will be able to have some of the molecules for use in future. There is also another very important molecule that is not mentioned here, what we call capsid inhibitor. So the capsid, yes, Doc Mambo. So the capsid inhibitor, the likes of lenacapavir, which is basically an injectable, which will be given to those clients who have multi-drug resistance, like in cases of the patient that we have been reviewing recently, patient with multiple drug resistance, and that will be more of an injectable. So there are tablet and injectable, which will be given 6 monthly subcutaneously. It's something that is already been rolled out because it has been approved by FDA, but unfortunately the drug is very expensive, quite expensive. Like a dose of 1 month will cost around 450,000 per patient. So there was the communities of people living in the HIV were petitioning Gilead, which is the manufacturer, to subsidize and also allow to share the formula so that we can have generic of lenacapavir to help curb the mortality due to a drug resistance. So that is it for the life cycle. Let's go now straight to this is just something that we have seen over the years. I don't want to dwell on it much. We can just check it later when I share the slides. I want to go straight to the HIV drug resistant testing. So what is HIV resistance? So HIV drug resistance is caused by changes, which we call mutations, in the virus genome that affect the ability of ARV drugs to block the HIV replication. So the whole aim of the ARVs is to block the viral replication. So when you stop the viral replication, then you stop the process of CD4 destruction. And if you stop a process of CD4 destruction, then you stop the disease progression. Now, if there is a mutation, I will talk about mutation. There are mutations that are advantageous and there are mutations that are disadvantageous. So we'll talk about them later, but basically, there are 3 main categories of drug resistance. So one is acquired, and this one develops when HIV mutations emerge because the viral replication among individuals receiving drugs. And this mostly occurs in patients who are non-adherents at the treatment. So a patient who is on treatment can acquire they can acquire HIV resistance in the process of taking their ARV medication. Then we have transmitted HIV drug resistance, which of course occurs when individuals are infected with HIV that has drug resistance mutation. And this should be the basis of talking to our PLHIVs we serve, that there is even if they are virally suppressed, if they don't use protection, if they don't use condom consistently, in case they have multiple partners, we don't encourage multiple partners, but in case if they don't use protection, they might get transmitted with an HIV resistant strain. Then we have those we call pre-treatment HIV drug resistance. So any drug-resistant virus detected in ART naive individuals. So someone who has never used ARVs, but when you do, there are countries that do pre-treatment drug-resistant testing. Kenya is not one of them, but basically, if you do a drug-resistant testing, which will be taken through next time we have such a series, you will understand how they are able to pick the drug resistant in a patient who has never used ARV. So those are the three categories that basically we have. Now, how does it arise? Back to my point again. So when you look at this is the ARVs, the anti-HIV drug. So once it is released, if the drug is working, it will be able to block the replication. So the aim of the drug is to stop replication of susceptible variants, which are colored in yellow, and I think this should be something like orange. So this is ARV that is working optimally. So it will be able to reduce the replication. So it will stop the replication, and in the long run, there will be viral suppression. Now, this other arm is where there is no blockage, because the ARV that you've given is already has some level of resistance, meaning the resistant variant will grow, and in the long run, it will become predominant. I will talk about, there's a slide I will talk about the difference between mutant virus and wild type of virus, and why it is very key to understand the two. So in the long run, because the ARV that we have given is not able to stop the replication, the virus that will be dominant in the blood or in the system of that PLHIV is the mutant virus. So basically, this is what we have just talked about. So you can acquire resistant in the line when you are, of course, in the process of taking ARVs, and then it can be transmitted from one person to another. So it is very, very critical. Now, how does drug resistant occur? So the most predominant ARV that we use as the backbone are NRTIs. Unfortunately, the HIV reverse transcriptase enzyme is a low fidelity enzyme, meaning it is prone to very many mistakes. And these mistakes are what we call mutations. And these mutations will lead to mutant strains of virus. So most mutations are inconsequential. We'll talk about that. Some result in incompetent strain of virus, meaning some mutations are advantageous. I mentioned that, and we will talk about which mutations are advantageous and which are not that are disadvantageous. So these mutations, some will confer resistance to currently available antiretroviral, and this is what we avoid. We don't want a mutation that will confer resistance to our ARVs, because that means we will not be able to achieve the viral suppression. So if you administer ARVs insufficiently, or you give insufficient potent drugs, then there will be selection of resistance, and this will become the majority strain of HIV in that patient. So basically repeating what you have just mentioned. So there are faster viral replication. Of course, if there's faster viral replication, it will lead to higher chance of HIV mutation. So the faster the replication, the higher the chance of mistakes. So, and remember, once mutation make HIV resistant to one ARV drug, it then quickly develop other mutations which can cause resistance. So basically, that statement is telling us it will not, the mutation, once some mutations occur, once they occur, they do not only affect that one drug, they can also cause drug to resistant to other drugs in that class. And that is very, very important. And especially when we talk about AZT. AZT is a very unique and a very it's a very unique ARV, because the thymidine analog mutations they can destroy the whole class of NRTIs at a glance. So we will talk about the AZT. So just one example that we have for a drug that not only causes problem to itself, but also spreads the problem to the other molecules within the class. We'll talk about that in details. So this is just a repetition of what we have covered. Let me talk about wild type of virus. And this one, I will be addressing some of us who have called me to consult on some of the cases. Now, the wild type of virus is the virus that has not been exposed to ARVs. So it's a virus which is ART naive. And this virus is very, very important to understand because it multiplies very fast, so that a patient who is suppressed today, if they don't take ARVs in the next 2 months, if you repeat a viral load after 2 months, there will be very high number of viral load. I was discussing this with one of our colleagues who was wondering why the patient 2 months was under LDL virus from another facility, and then 2 months down the line, the patient has the client has a viral load of millions copies. Yeah, because of wild type of virus. That tells you basically that patient is not taking ARVs. If you are taking ARVs, they're able to contain the wild type of virus. Now, let's talk about resistant HIV. So resistant HIV virus is kind of slow in the replication. If that person is adherent to the treatment and they have resistant strain of the virus, if the virus, the predominant virus is the resistant one, it will not be as high as if like in case of wild type of virus when it is dominating. So that tells you, that can help you to tell if your patient is taking ARVs or not taking ARVs. Because if they are taking ARVs, then the virus should come below 10,000. If they are taking ARVs and they have resistant strain which is dominant, the viral load will not be in hundred thousands, it will not be in millions, it will be around 10,000 there, because the resistant mutant virus does not replicate as fast as the wild type of virus. That helps you to make a decision. So poor adherence will lead to drug resistant, and drug resistant will lead to regimen failures. Basic knowledge. So what causes drug resistant? I am tempted to skip this because I have another slide, but let me talk about the main things here. So poor adherence, insufficient drug level, viral replication in the presence of drug, and resistant virus. So let me I will talk about the different causes of the drug resistance. Now, what is it about the replication? So after someone acquires HIV, it undergoes replication. And we said reverse transcriptase, which forms the large part of our ARVs, is highly error-prone enzyme, and it may cause many mutations. So every cycle, there is a mutation. Every cycle, there is a mutation. These mutations are completely random and by chance. You might not be able to control them. So there is, of course, rapid turnover of virus, which will cause a high maturation, not maturation, but mutation rate, which can be approximately 1 billion virus particles per day in HIV, one infected individual. So ARV failure and resistance. So viruses might acquire drug resistant to one drug and can develop mutations leading to multi-drug resistance. That's a repetition of what we said. And this one is worsened with continuation of a failing regimen. And that is why we always encourage a patient to be kept on a failing regimen for long. Remember, HIV does not forgive treatment errors or the non-adherence, meaning ARV resistance, once it occurs, is lifelong, since resistant HIV can hide in latent cellular reservoir for many years. That is what we call archived mutation. You will hear when we're interpreting the drug resistant test, we'll talk about could be the picture that we are seeing is not the right one because of archived mutation. So the mutations, the resistant HIV is able to hide. The moment you stop taking that ARV, it hides in the reservoirs. Then when you give that client the same drug later in life, it will come out. These are the factors that I wanted to describe, what contribute to ARV failure and resistance. So on the virus part, so if you have a high replication rate of around 1 billion copies per day. So we also have RT, which is reverse transcriptase enzyme. If you have a client who is on NRTI, which is NRTI or NNRTI, which is basically a reverse transcriptase enzyme, the drugs that target the reverse transcript enzyme. So these viruses, they tend to replicate very fast. Then, of course, we have the latent reservoir of HIV. So if you have many latent reservoirs, then the more risk of developing resistant. On the area, on the side of the host, if the adherence is below 100%, if there is toxicity or inconvenience, that may also contribute to drug resistance. Then on the drug side, we have inadequate potency. So if you give a drug of less potency, inadequate durability, a drug that wears off very fast, a drug-to-drug interaction, poor tolerability, inconveniences. So all that will lead to drug resistance. Remember, one or more of these factors can lead to ARV resistant in given patient. And this point is very important because you might be focusing on adherence only, and your patient is taking atazanavir with maybe omeprazole. So they have a chronic gastritis or PUD. He or she is on atazanavir, and now your focus is on adherence. Maybe they are 100% adherent, but because of drug-to-drug interaction, or you have a client who is not tolerating the drugs. They are taking, yes, but they end up vomiting, something like that. So you need to be look at it, not like one-sided. You look at broadly so that you're able to pick the cause of the treatment failure. What about the HIV mutations? So HIV viral mutations may affect they may cause what we call phenotypic effect, whereby we just need to understand these terms because we'll use them in the subsequent presentation. So virulence, the viral virulence is the ability of the virus to invade a cell, while the viral fitness is the ability of the virus to compete with wild type of virus. And then the immune response is where HIV may escape antibody and CD4/8 immune control. So the virus is basically is not controlled by the antibodies that are produced against it. Then when we talk about transmission efficiency, so some mutations are more, they are more efficient when it comes to transmission, so you can easily transmit them. Then hypersusceptibility basically means there are mutations that lead to a better effect for another drug. I will talk about that, like in case of M184V mutation, it increases the susceptibility of TDF and ACE2. So it's an advantageous mutation because it increases viral susceptibility. So the presence of that mutation, you can tap it to help in improving the other molecule that the drug that it is administered with. So this is just a repetition of what we have covered, that ability of HIV to generate new virus variant allows virus to evade immune system and foster development of ARV drug resistance. So drug resistance, the consequence of viral replication in the presence of ARV will, so the resistant may, some resistance may require a single mutation, like in case of a drug like nevirapine. We'll talk about that, like K103N mutation. Then there are mutations that will require, there are resistance that will require multiple mutations to confer resistance. We'll mention some before we finish this CME. So we have virus-related factors which lead to resistance, and these include high replication rate. So if you have a virus that is highly replicating, then that virus is more prone to developing mutations. If you have frequent errors which are made during replication, like in case of reverse transcriptase enzymes, then the frequent errors of the virus may of course lead to development of mutation. Then we have those who drugs, but not drugs, but virus that have high mutation rates. So they can even have 20 billion mutations in a day. Then I remember we talked about the presence of latent reservoirs of HIV. So that now the drug resistance that has occurred in 2023 or 2024 can be archived, can be hidden in the latent reservoir, and you might get it later in life, maybe 20 to 30 years. So it is archived. And when you do a drug resistant test, you might not find it because of it has been stored in the latent reservoirs. Then we have virus and drug-related factors that cut across both the virus. So we talked about latent reservoirs, and we said that ARV resistance, once it develops, it's probably lifelong. I mentioned that. And of course, the resistant HIV can hide in latent cellular reservoir, which can be activated many years later. Just a repetition of what you have just mentioned, but to emphasize on the importance of understanding this. Once a patient is resistant to an ARV drug, that drug will probably be ineffective in future. So if and I will talk about the importance of a previously done DRT. So a DRT that was done in 2007, is it relevant in 2024? The answer is yes, because you might be able to pick a resistance that occurred in 2007, which is still relevant today because a mutation is lifelong. So if you want a high level resistance to isn't in 2007, the status still remains the same. Nothing has changed to the positive. So the HIV, if you mentioned this not once, not twice, that it does not forgive treatment errors or non-adherence. We keep emphasizing on that point because it is very, very important for all of us to understand. We have now the viral mutation and the genetic barriers. So antiretroviral genetic barriers. So we talk about efficacy of ARV treatment regimen depends on one, activity of the regimen, individual ARV drugs, and the genetic barrier. That is, a number of HIV mutations required. So some of the drugs will require a number of HIV mutations. Others will require just one mutation. So basically, genetic barrier means the number of HIV mutations that are required for a client to develop resistance for each of the ARV molecules. Now, let's define mutation. So mutations can be, you can define it in molecular. So we have molecular definition and biological definition, which are kind of related. Molecular definition of mutation is the change in nucleic acid sequence compared to a reference sequence. So there is a reference sequence of a virus, of a virus that is non-mutant. So the change in the nucleic acid sequence, we'll talk about that, is very, very key for you to be able to pick the resistance. Then biological definition is change in nucleic acid sequence. Now that results in change in structure or function of the nucleic acid or a resulting protein. So whatever you see there, these are amino acids. So these are the codon. So the next slide will put it better, but let me just preempt that for mutation, like in this case of what we have here. So we have a long structure of a peptide, which has different amino acid at different levels. So like, for example, when you talk about M184V, so M is an amino acid, methionine. So it's methionine, which should ideally be found in position 184 of the viral peptide. But if it's a mutant, the methionine is replaced by a V, which is a valine, which is also another amino acid. So if you're doing a drug resistant and you are sequencing the polypeptide of the virus, and you find in position 144 the amino acid that is you find the amino acid is a valine, then that means it's a mutant, because ideally in a reference sequence you should find a methionine amino acid. So basically that's what it means. So some mutations are silent, like in case of so we have lysine, and then we have the aspartic acid, and then we have serine. So this one is a normal structure. It's a normal structure of a virus, but in a mutant one, you'll find that the lysine is replaced by the asparagine amino acid. So if it is able to replace the whole of the structure, then it becomes a mutant or a mutation that is visible. Then we have a silent mutation, like in this case, which did not change. So the serine remained a serine. So I hope you're able to get the basics. But this is what I was explaining, that in PR, let me use my pointer again. So in protease peptide, you will find amino acids in position 1 to position 199. Then in RT, you'll find amino acid located in position 1 to position 540 of the amino acid. But it doesn't mean that it is located in all the positions. There are specific position, like when you talk about M184V, the example that is given here, if you find M in position 184V, if you find M, which is methionine amino acid in position 184, that means this is now the reference. This is the ideal. This is the wild type of virus, which if you give the ARVs, if you give DRT to this client, they should be able to have virus suppression, because it should be working, because it is the right amino acid in the right position. So in position 184, in position 184, you find M, you are good. But if in position 184 of codon, or the amino acid structure, if you find valine, then that becomes a mutant amino acid. So that if you have a M184V, then this is a mutant virus. So this virus will have what we call, so we have a mixed mutant, whereby you have a mixed mutant and wild type of virus. So in this case, if you find in position 184, you find both methionine and valine, then that becomes a mix of wild type of virus and the mutant virus. And in position 184, if you find valine and the isoleucine, then it is a mixture of two mutants. So instead of finding, instead of getting M at position 184, if you find valine and isoleucine, someone is talking. If you find valine or isoleucine, then that becomes yeah. So someone was making noise. So that makes it a mix of two mutants. I'm almost done. So sorry about that. Now, what are the effects of nucleotide changes? So nucleotide changes, which are basically mutations, will cause change in amino acid sequence of a protein. Then this change in the structure, then the change in amino acid sequence of a protein will cause change in the structure and function of the protein. Like, for example, viral enzyme protease or reverse transcriptase. So the viral enzyme protease will undergo because the virus had undergone mutation, these enzymes will not be working. They will not be working normally. so that when you give a protease inhibitor, then that process, the virus will be able to evade that blockage that comes with the inhibition of protease molecule. Same case with reverse transcriptase. And this will lead to changes in ability of drug to inhibit target enzyme, and this will result to resistance. So this is just a summary of what we have covered. Let's talk about low genetic barrier and high genetic barrier. When we are reviewing cases, you hear us most of the time talk about this drug has low genetic barrier to resistance. Then we hear us talk about, but this one has high genetic barrier to resistance. I'll give you an example. Let me use an example of NNRTI, like nevirapine, for example. So nevirapine has low genetic barrier resistance, same case with 3TC, same case with FTC, which are basically, they have the same structure. So for certain ARVs, only one mutation is needed to stop the drug from working. For example, in case of K103N, an NNRTI mutation will cause an nevirapine to stop working. That is why, that was one of the reasons why we phased out the likes of nevirapine, because of the low genetic barrier to resistance. Because if you miss the ARVs, if you have poor adherence for just 1 week, then you end up having case K103N mutation. So that's just basically the explanation. This lysine, the aspartic acid, they're just explaining what K103 is all about. Now, we have other ARVs that require multiple stepwise mutations. So not only one mutation, but several mutations must occur before the drug loses the effect. Like in case of I47A, which is a protease inhibitor mutation, you require 2 base mutation change. So you can see we have this amino acid isoleucine, which will not only change at this position, but this and this. So the whole of this structure must change from isoleucine to alanine for it to acquire a mutation. So that means does not only it does not occur easily. So you have to work very hard. That is the word I like using. You must work hard for you to get I47A mutation. So if you get I47A mutation in drug resistant test result, you know that patient was non-adherence to the treatment for a very long time to develop such a very strong mutation. So single mutation and resistance. So this is just a basically of with just repeating what you have just covered. So I'll skip that. And this one is just the same. So you require multiple mutation for you to get drug resistant. But let me talk about this. So the longer a failing regimen is continued, the greater the number of mutations which will occur and which will lead to greater resistance, including cross resistance. Very important. So the moment you get your patient as a viral load done in 2018, 2019, 2020, 2021, they are still non-suppressed. That patient is accumulating mutations, which will lead to cross resistance, so that a patient who has never been exposed to TDF will end up with high level resistance to TDF when you do a drug resistant test. Just a repetition of, so we have primary mutations which decrease drug susceptibility. Then we have secondary mutations that are selected after the primary mutation may have a limited or cumulative effect. Then we have multi-drug resistant that can decrease susceptibility to many or all drugs, so that you'll get a client who will have M184V mutation, which is the most common mutation anyway, but they do not have mutation in other positions, because those are some of the first mutations for a client to, or the virus to to develop. Now, this is very important. I think I will take some time here because this one it helps us to understand why we prefer some of the why, and this one informs why we prefer some of the combination than the others. Now, this y-axis is talking about potency, like estimated log change in viral load. Like if you give someone DTG containing regimen, how many logs do you expect to suppress within a very short time? So this is the part, the potency part, the rapid reduction in viral load. Then on the x-axis, we are talking about genetic barrier to resistance. So approximately the number of mutations needed to cause treatment failure to that molecule. Let me start with, I mentioned nevirapine, the emtricitabine and lamivudine have low genetic barrier to resistance. But in terms of lowering the logs, they are able to lower at least 2 logs within a very short time. Let's talk about rilpivirine. Rilpivirine is a NNRTI, which is part of the long-acting carboneva that is undergoing. I saw they released some the progress report on the clinical trial that is ongoing on the rilpivirine. So rilpivirine is a very good molecule, but you can see it doesn't look so good in terms of genetic barrier to resistance, even though it is able to lower the viral load logs, but in terms of still require less than 2 mutations for you to develop resistance. Now, we have this the RAL, forgetting the name of this, but this is it's an NNRT, not NNRT, it's an INSTI. So the red colored, this color is, I don't know which color is this. I've lost my presentation.
Yes, we can no longer see your presentation. It's back on.
Okay. So I think I've pressed on the stop share. Okay. So I'm talking about these. These are INSTI and their fibers. Now you know why. During the years of 2014 to 2018, we were preferring efavirenz. Yes, it has low genetic barrier to resistance, but it is able to reduce the viral logs, or it is able to cause viral suppression within a very short time. They can reduce 3 logs within a very short time. Now, RAL compared to DTG, and that is why we no longer use RAL. RAL compared to DTG, and especially after we got DTG for pediatrics, we don't need RAL because DTG has high genetic barrier to resistance, and also it rapidly reduces the viral load within a very short time. Now let's talk about AZNT. AZNT, you require at least 2 mutations to develop resistance. However, it is very slow in terms of the viral suppression. So it takes time to get viral suppression when client is on AZNT. ABC, TDF, they have similar resistance pattern. We'll talk about that in the subsequent CMEs. But TDF, you require at least 2 mutations for it to develop resistant, but it has some advantage in terms of the number of the logs that you reduce within a short time. So if you combine TDF, 3TC, and DTG, then you have a combination of drugs that have different genetic barrier to resistance effect and also the potency. Let's talk about darunavir. Why is darunavir very far? Like it is able to reduce viral suppression. It is also cause viral suppression very fast, and also it requires at least 4 or more mutations to develop resistance, and that is why most of our third line patients our clients are on darunavir-based regimen because of its potency and its high genetic barrier to resistance. I think this should be my last slide. So I wanted to talk about archived mutation and what we talk about normally and most frequently you will hear us talk about inadequate drug selective pressure or drug pressure. How does it happen? So remember, resistant testing should be done while the patient is taking ART. Or if that is not possible, within 4 weeks after discontinuation of non-long-acting ARV drugs. So you either collect it when the patient is taking ARVs or within the 4 weeks of stopping. That is why we were talking about when we were transitioning our client from LPVR, we were talking about you collect a sample, then change the client to another regimen. Because we know if you don't do that, we will lose the mutation that had already conferred by the LPVR. We'll lose it if we stop taking, if we don't take the viral, not viral, but DRT at that point and take it in future. So if you take it 1 month after stopping, then you don't expect to get any mutation. So the drug will get what we call a false DRT because of archived mutation. Now, if 4 weeks have elapsed, resistant testing may still be useful to get therapy. However, previously selected mutations can be missed, what we call archived mutations, due to lack of drug selective pressure. I know Elfas will talk more about the importance of ensuring that by the time you send the sample to the lab, it has enough drug pressure. Now, the absence of detectable resistance in such a patient must be interpreted with caution when designing subsequent ARV regimen, as mutations may decay with time. Now, we were in a meeting last week on Thursday. The meeting was for, I think, facility, I think Dadora 2 health center. We were discussing some DRT, and I remember telling the participant in that meeting, the people who were attending that meeting, that the DRT that was displayed was useless. Why? Because by the time the sample was being collected, the patient earned, I think, around 150,000 copies, if I remember well. And that client had IVL from, I think, 2018 to 2020. Since they were put on TLD, they have never suppressed. Now, when we got that DRT, you expect at least to get even M184V. Because M184V, you require just one mutation to develop resistance. So if you don't get M184 in such a patient, you already know that by the time they were collecting that sample, patient was already not in ARVs, and that the most dominant virus was the wild type virus, which will come out susceptible anyway because it has not been exposed to ARV. So that explains why we need to be very cautious when we're interpreting DRT, and especially a DRT that comes very clean, a DRT that comes with all the molecules susceptible. That you need to be very cautious before you give it a clean bill of health. So all prior and current drug-resistant testing results should be reviewed and considered when designing a new ART regimen for a patient experiencing virological failure. That is what I mentioned, that a DRT that was done in 2007, it is still relevant in 2024. It will still be relevant in 2050 because it has because of the basic knowledge, the basic principle that once you develop a resistance, you can never go back. If you are intermediate resistant, you can only go to high level resistance. You cannot go back to low level resistance. And in case you get such a scenario, you know that there are archived mutations that you are missing. Now, last point, drug-resistant mutations may decay with time, and mutation detected in prior resistant tests may not be detected in current tests, though they remain clinically relevant. So, if you are consulting, if you are, 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 if you are and you have a drug resistant test that was done previously, kindly attach it. It is very, very key for clinical relevance. That marks the end of my presentation. Back to you, Chair.
Thank you very much, Chris, for that introduction and overview. I want to believe that as we proceed with the subsequent CMEs, the things that seem strange to some of us will make more sense. And probably our participation in interpretation of some of the DRT results will also help us to understand better. So we have a few questions already on the chat. The first one is, do we have the capacity to do DRT to eligible clients? Then I can give you two. Then another one is, considering the fact that 3TC has a low genetic barrier to resistance and its viral suppression isn't that good, why is it kept as a first-line drug? Actually, it is kept as a consistent part of all drug combinations. So maybe you can address the two of those.
I think you can add two more if we have.
Okay.
Yeah, so that
Okay.
these are very easy to address.
Does timing of drugs, especially BD dose, contribute to development of mutation? Then the other question I have is, we have said that when you continue a failing regimen for long, the greater the number of mutations that will occur, and it will lead to greater resistance. Yet when we take samples, we actually ask the staff to continue with the failing regimen. Are we doing them more harm by saying that, or that is a safer bet compared to stopping as we wait for the appropriate combination of medication? So you can address those.
Okay, thank you. Those are very, very, very relevant questions, and I'm glad that they have come out, meaning people are following this conversation quite well. Now, as a country at the moment, do we have a capacity to do DRT? The answer is no. Because from March last year, March 2023, we have had supply of DRT commodities in our main lab, which is NHRL. I know we have had some support from UON Faria Jami to undertake some DRT that we've already done, around 69 of them. But for the National Reference Lab, the answer is no, we are not doing DRT at the moment. I might not be able to answer that fully because that is more technical. It of course requires people at the higher level to respond to it. But the point that we have at the moment and the guidance that we have from the national program is that we can still keep approving DRTs. The national program or the national lab has capacity to store the DRTs, and when we get the commodities back, they will be able to run those and give us a result. So that is the status at the moment when it comes to DRT. But I know some of the regions like the South Rift, they are doing their DRTs with support from their implementing partners at Kericho, Cambridge Lab. So yeah, that is the answer.
So then, Chris, I'll modify your response and say, yes, we have the capacity, but we currently don't have the commodities.
Yes. That is the point. Yes. Thank you for.
So it should not hinder us from collecting the samples. We have been informed that they can store them until we have the commodity.
Yes, thank you for that clarification, Dr. It's very important. Now let's talk about 3TC. I'm tempted not to respond to it because I know there is a whole around 3 slides explaining why we keep 3TC, but just a summary of that, because someone who is in this call might miss in the other one. 3TC and FTC are very, very unique molecules. They confer a mutation we call M184V, and M184V is a very, very interesting mutation. And this M184V mutation is what makes us keep 3TC, you will find it in first line, in second line, third line, wherever, unless a patient who has maybe renal problem and we are not able to give a 3TC. Those are the times that we avoid 3TC, and some of the patients who end up not tolerating 3TC. But M184V is a very important mutation because, yes, it causes around 200 to 300 times. It reduces the virus susceptibility to 3TC and FTC by 200 to 300 folds. That means if you give 3TC or FTC in presence of M184V, it is useless. If you give it as a single molecule, it is useless. However, the M184 presence increases or causes what we call hypersusceptibility to AZT and TDF. So meaning the presence of M184V will make our TDF more effective, our AZT more effective. However, it causes a reverse to ABC and the didanosine, which we no longer use anyway, but ABC is a drug that we use mostly, especially in our children who are less than 30 kgs, and in our clients who have renal issues, because we don't have TAF yet. I know TAF is coming. That will be a very good progress. So it will reduce around 2-3 times virus susceptibility to ABC. And that is why we are not encouraged to use ABC, because ABC, remember, M184V is the most abundant mutation. So you will find it in around 70% of our patients. They have it. So in the presence of M184V, you will continue making your ABC more resistant. So that's why we avoid. And that is why when our children reaches 30 kgs, we transition them to TDF, because we know keeping them on ABC, you are not doing them, not giving them the right, the optimal. The other part, which is very, very key on 3TC, the M184V produces what we call unfit virus. The unfit virus basically means virus that are slowly, or they are slow when it comes to replication. So it's kind of produces virus that can easily be eliminated by other molecules. So that is why we keep 3TC. I hope that one answers your question. I know I will emphasize the same the next time we do the CME. Now, the timing of BD dose, very important. Remember, there is a reason why we give drugs 12 hourly, and others we give 24 hourly, and then there are those we give even monthly. It all depends with the half-life of these molecules. How long does that drug remain in the circulation? So if you are giving someone AZT and you give it AZT and give it in the morning and you don't give it in the evening, then that means by the time it reaches the time for the next dose, the AZT that was given in the morning has already worn off. And if it has worn off, that means this patient is off the drugs. And that is when we give a chance for mutation to occur, because the virus now will try and mutate so that it evades the molecule when you give it next time. So it is very critical to ensure that you give the timelines of giving ARVs are adherent to completely. Now, question number 4. Why do we keep drug? Why do we continue ARVs even when we know it is detrimental to do so? Now, the question the question here is, what is the risk of stopping ARVs as we wait for us to do the adherence, blah blah blah, and then switch vis-a-vis keeping the regimen? Now, if you stop, there is something we call, I'm forgetting the name, but the viral replication will be very fast. Just keeping that client on a filling regimen is not good, but stopping ARVs is not good because of there will be rapid viral replication. And that will, remember the viral replication also occurs and also has problems in terms of, number one, the destruction of CD4. I'll give you an example. A client who has multiple drug-resistant mutations, if they adhere to the treatment, they are able to suppress the viral load, not really to below 1,000, but they can be able to contain the virus to below 10,000. A viral load of below 10,000, you cannot compare it with a viral load of millions, like 5 million, because the 5 million viral load is destroying CD4 very fast. So that now this patient, yes, you have stopped the ARVs because you want to preserve them, but they are destroying CD4 very fast, such that your patient might even die before you get a molecule that will be functional. So it's a less of which is a lesser evil to do, keeping or stopping ARVs. I hope that answers your question. But we hope that during that process of keeping that client on a filling regimen, you are doing something about it, including ensuring that adherence is a key thing that you are following, so that in case there are some level of activity in those molecules, then they should be able to suppress the viral load. I hope that answers the fourth question. Back to you, the chair.
Thank you. Thank you for your feedback. A few more questions. From your presentation on potency and genetic barrier, what is the science behind using AZT nevirapine for hay prophylaxis? And I'll combine that with another one that asks, if a mother fails AZT-3TC nevirapine, will AZT and nevirapine be effective prophylaxis to the hay? That's one question. Then another comment is, it means then for PIDs who take ABC-3TC DTG, the most potent drug here is DTG. The third reaction from Nixon says, thank you for the update on factors that lead to viral ART resistance. Going forward, is there a possibility where doctors can be allowed to increase or decrease dosages to be tailored according to client clinical presentation, other than just working with standard regimens?
How many questions do you have? Because of the time is much gone. We might be able to. We might be forced to respond to some next time.
That's all. There's
good.
the one on there's the one on AZT nevirapine.
Yeah.
As hay prophylaxis, whether it's effective, and if mother had failed on AZT-3TC nevirapine, whether it would be effective. Yeah. Then there's a comment on the combination of ABC-3TC DTG for pediatrics,
yes,
where it seems that the only potent drug is DTG. And the third feedback is there a possibility for us to increase or decrease drug dosages, tailoring them to client presentation, other than working with standard regimen?
Okay, thank you. I think if we respond to those, we will now meet on Wednesday next week. But let me just try and respond to this. AZT and nevirapine prophylaxis. I will give you a practical example, a very practical example. So you have a client who was on TLE, then developed treatment failure, was put on AZT, 3TC, and ATVR. Let's even use ATVR. Developed resistant or developed treatment failure, now was put on TLD, maybe plus darunavir. And this patient is viremic. Let me use the one viremic, meaning they have a viral load of above 200. Let's even say a viral load of above 1,000. The question is, if you give, and this is a mother who is pregnant, going to deliver and start breastfeeding. Let's say the mother is breastfeeding, for example. As IVL on that line, failed TLE, which has efavirenz, which is basically similar to nevirapine, failed AZT, high level resistant to AZT, which is our one of the prophylaxis that we do. And now the client is on that line and viremic. Well, that mother this one, I hope Kibanda is in this call because it's very important. Will this child, will there be prevention of mother to child transmission in this case? The answer is I don't know. That's the answer I can give. I don't know. Why am I saying that? Because there are no studies that have been done. I haven't seen any. There is any study that is out there. Maybe we can check. I haven't seen any study that support or that of course does not support the use of nevirapine and SNT in such a client. But the basic knowledge is obvious. Will nevirapine and SNT work? When you look at how the mutations are structured, the answer is most probably they will not work. So, and that is a question I know we have raised in the national program, and we are waiting to hear what is the next in terms of guidance on the use of nevirapine and SNT. I don't have an answer to that. Let me go to question on why do we give ABC, 3TC, DTG, and by giving this, the only key drug is DTG. The answer is yes, we know ABC as is inferior to TDF, but unfortunately we are not able to give TDF. And remember, we no longer use SNT as first line, and I will explain why we don't use SNT as a first line. We don't encourage. So ABC is a good drug. Yes, it is inferior to TDF, but it's a good drug. So the only thing that we need to put into consideration and we need to tell our client is that these drugs, even the DTG, even the Runavir, will only work if you take them. If you don't take them, they will not work. So even the ABC that seem to have issues with the M184V and the K65R, and there is another mutation I'm forgetting. There are around 3 mutations that, and plus also terms. Even in the fact that ABC is affected by this, if you take them, the ABC, and we have seen it, we have seen very many of our adolescent transition to TDF, they have never had any viral load, high viral load while on ABC3TC, DTG, or even ABC3TC lopinavir that we were using previously. So it's a matter of adherence. If you adhere well to the treatment, it will work. If you don't adhere to the treatment, even DTG will fail. We have around 15, I think 10 to 15 clients who develop high-level resistant to DTG. It's a magical drug, but it can only be magical when you take it. Same case with darunavir. We have very many patients who have high-level resistance to darunavir. That is the key word is take the drug, it will work. Now, how can we be allowed to increase the doses, like for example, TDF or maybe 3TC or DTG, if you feel like this one is not working? So my response to Nixon is that the problem is not the dose of the TDF, the problem is not the dose of 3TC, and the problem is not the dose of DTG. The problem is the client is probably non-adherent, or there is a reason why the drugs are not working. So you need to work on that reason, the cause of that problem. Like for example, if client is on TDF, which is 300 milligrams OD, how high can you go without killing the kidneys? Yeah, you know. So I know phenotypic resistant testing will tell us the level of, like for example, if you have a high level resistant to DTG, if you do phenotypic resistant test, it will tell you how many folds can the DTG, even at that level, be able to reduce, so that now you're able to recycle, or what we call salvage therapy. But that one will be explained better by an expert in the field, what it means. When you do a phenotypic drug resistant testing, the result comes as this drug is potent at this level. So maybe that one might, but I know the dosage might be very critical because of the toxicity. But I know for DTG, even in the high level resistant, we give it twice daily and it works. And also, we also have darunavir, which when we have high-level resistant to darunavir, we recycle, but we give it twice daily, and it has shown to work. Yeah, so I think that marks the end of the questions. Unless there's one burning because of time, it's already.
There was one on whether we can adjust the doses based on client clinical presentation.
Yeah, I think I've responded
Other
to
than
that.
using standard. Okay.
Yeah, I've responded to that.
Just a few comments from Casco Nairobi. It says emphasize on need to do EACs for a maximum of 3 to 6 months before switching from a failing regimen. And he also says that resistance occurs in infected individuals. Nevirapine for children is used as a prophylaxis, and asks us to refer to the initial slides of the drug cycle. A number of attendees have asked for the slides, the presentation, and I'd just like to let you know that as long as you registered, the slides will be shared with you soon. I believe that's it. That's the end. Thank you all for your participation, your presence, your interest, and thank you, Chris, for being with us. Let's continue being on the lookout for the subsequent CMEs so that we piece together all the information and it enables us to be better equipped in handling our clients. I'll request one of us to wind up this session with a word of prayer, a volunteer to close this meeting for us. Anybody? Thank you, Sandra. Anyone to close for us with a word of prayer? Okay, let's pray. Heavenly Father, we are grateful that you have been with us through this meeting. We thank you for the opportunity to learn. We pray that we internalize this information and that we use it effectively for the management of our clients. We thank you for each and every healthcare worker present here. We ask for a blessing upon them, even as we continue with our work for the rest of the day. Bless the work of our hands and be with us until we meet again in the next series. This is our humble prayer in Jesus' name. Amen.
Amen. Thank you.
So thank you, everyone. Have a good day. See you next week for the next CME. We are free to leave.